Okay, I think we can start. Hello everyone, I'm Florentin, and I'm here today with my colleague Raresh. We are both software engineers at Adobe, and we'll be talking today about how we are handling billions of events per day with Kotlin Coroutines. Raresh and I have been closely working together for the past 7 years, and our main focus has been on developing and maintaining real-time data-intensive applications. Along the way, we have been using different technologies that would allow for millisecond latency and high throughput. And in the synchronous processing realm, we have been using from the good old callbacks to features, reactive streams, and even the actor model. In 2019, Kotlin caught our attention, especially due to its synchronicity approach with coroutines and structured concurrency. At that moment, Kotlin was not so popular for Okay, thank you. Kotlin was not so popular at that moment for server-side development as it was for Android, but we started to use it in some of our applications and even building new ones entirely in Kotlin. And in 2020, we decided to migrate one of our main applications, which is handling billions of events per day, from a blocking to a non-blocking model using Kotlin and its coroutines. The main goal was to increase the throughput and while decreasing the costs, and of course, in the process, to also prove that Kotlin scales, that Kotlin and its synchronicity approach scales for large enterprise applications. To give you a sneak peek, we were able to almost double our throughput while obtaining a cost decrease of 25%. So stay with us to find out how we did it. Our presentation has conceptually two main parts. In the first part, which will be Kotlin-centric, we'll have a deep dive in how we leverage Kotlin to turn the application non-blocking and have a working proof of concept. While in the second part, we'll focus on how we productize the POC and manage to safely release it to production. So this part will be more generic about asynchronous applications and the challenges you can face and how to overcome them. The application that we migrated is part of Adobe Audience Manager, which is a data management platform globally distributed across 8 clusters and that handles 50 billion requests a day. The goal of the application is to collect data and build anonymous user profiles, on top of which our customers can categorize their users in audience segments in order to improve their online experience. To better understand what the application does, let's have a look at how a request is processed. A request comes in telling us that user with ID 10 is on the cars page. Based on the user ID, we are reading multiple connected profiles from our database, from where we are retrieving existing segments, like S1, which is telling us that the user favorite color is green. After that, we are re-evaluating all segments, which are Boolean expressions, in order to possibly categorize the user in new audiences. And finally, we are saving them in our database. Based on these audiences, our customer can deliver to you a custom personalized experience. For example, they can show you a green personalized car, of course, if you are part of the S3 audience. We can observe from the request processing model that we are doing a lot of I/O operations, which are blocking, and this is why we decided that a suitable performance improvement would be to turn them non-blocking. Now let's have a look at how our application is structured. We have a Java web application which is using Jetty as an embedded server that has 4 main components. Filters, which provide common logic for all requests. Controllers, which are handling requests on a per route basis. Business logic, which is used by all controllers. And the data access API, which provides access to our database. In the first part, we'll focus on how we turn the components on the left-hand side on blocking, and then we'll have a deep dive in the data access part. Our strategy was to keep changes to a minimum, and this is why we decided that for the data access layer to not change anything, because it already provided an asynchronous API via Eric's Java reactive bindings. For the business logic, which was performing blocking operation on top of the results from the data access layer, we decided to propagate the same API upstream. While for the web server, we decided to replace Jetty with Vertex, completely rewrite the filters in Kotlin, and for the controllers, just to translate them into Kotlin to be able to use suspendable functions. So let's have a look at how we did it. We were using an old Jetty version, and we needed to do the upgrade in order to be able to leverage Jetty's asynchronous request processing model. And then we will be required to bridge it to work with Kotlin Coroutines. So we decided to replace Jetty with a more Kotlin-friendly framework, and our choice was Vertex as it offered Kotlin bindings. The setup is simple. We create a Vertex instance, we create a router where we define our routes and call our controllers, and then we start the web server. Now let's see how it actually made the application on blocking. Here we have one of the business logic functions, which is evaluating those audience segments that we talked earlier. And we can see that it performs a blocking operation when reading profiles from the database. We turn this non-blocking by keeping the implementation in Java and by changing the function signature to return Eric's Java reactive construct, in this case a single. We chose to showcase this simple example where we just use the map operator and we are done. But in reality, we really had some complex cases which really challenged us to turn them non-blocking, and frankly kind of got why blocking operations were used instead. This is a controller. It implements an interface which has a single method called handle that receives the request and returns a response. It performs blocking operation when interacting with a database, like reading identities, and also when interacting with business logic functions, such as the one we just changed. For the controllers, we used IntelliJ's automatic Java to Kotlin translation, and then we made the handle function suspendable so that we can use the Kotlin Coroutines Eric's Java bridge to replace the blocking operation with await operations, and we can see the nice suspension points there. Now, we are done with the transforming, so we needed to plug the controllers into the Vertex router, but as we all know, we cannot simply invoke a suspending function, we need a Kotlin coroutine to do so. So we'll have a generic route definition, which will launch a coroutine on Vertex event loops threads. So basically, each request will be handled by its own coroutine. Firstly, we'll get our router via dependency injection, and this router will be able to tell us which controller to use to properly handle the current request. And this is why we are having a single route definition. After we have the controller, we can handle the request and return the response. Everything looks good, but we actually had a few challenges. And one of the main challenges has been how to continue to do request scope dependency injection in a synchronous world. It is not clear at the first glance, but most of our classes are ending up to be request scoped and get instantiated for every request. For example, we had our router, which we are getting via Juice, our dependency injection library, and that is able to tell us which controller to use, right? But as we can see, we do not explicitly pass the current request because it is receiving it in its constructor, so it's defined as the request scope class. And the question is, how did this work before? I mean, in synchronous processing, a request is handled by a single thread. And Juice had a servlet filter, which was leveraging a thread local variable to cache all those request scoped instances. In asynchronous processing, now we have a coroutine that handles each request, but a coroutine can run on multiple threads. So how could we solve this? We've been thinking about rewriting our controllers and business logic to get rid of the request scope dependency injection, as we consider that it is an anti-pattern, but it would have been too much work, and it didn't match with our initial goal of keeping changes to a minimum. For example, here we have like 50 classes that were injected only in this controller. So what we need is a mechanism to load some context in a thread when a coroutine is resumed for execution on it, and a method to clean up that context when the coroutine finished its execution. And Kotlin Coroutines provide such a mechanism via the thread context element. So we implemented a class that extends this mechanism, and will be leveraging also a thread local variable that will be populated and cleaned up on every thread where the coroutine will run. And the two methods that we need to implement are the updated context, in which we retrieve the whole context and return it so that we'll be able to restore it later on the cleanup phase, and we are setting our own context. And in the restore thread context, we just set the old context we returned previously. Now, we also need to make juice coroutine aware, right? Because we need to make juice use the same thread local variable that we referenced before. So when an instance is requested, we look it up in the cache, and the cache is our thread local variable. If it is present, we just return it. And if it is not present, we need to instantiate it for the first time and also cache it so that during the same request, we continue to return the same instance. Now the final step is to add the thread context element to the context of the coroutine that is handling each request, and we are done. We've solved our problem with the request scope dependency injection in an asynchronous world. All this work, plus rewriting the filters completely in Kotlin, took us 2 intensive full Fridays of pair programming. And what we achieved is a working, apparently non-blocking version. But I'll let Raresh deep dive in the data access part so that you can see if our journey was so smooth as it seems.
Thank you. Hopefully you can hear me now. So data access API was the part of our application that enabled us to talk with our database, which were Cassandra clusters. It was built with Eric's from the beginning, and we thought that was our advantage here. If we could ensure this part is non-blocking, then we could have the entire application non-blocking end-to-end. The reason for using Eric's here stemmed primarily from the need of running multiple queries in parallel, as well as on multiple Cassandra clusters. Think of active, passive kind of setups. We are also enforcing timeouts on all our queries since we are very sensitive with the overall response latency. So Eric's really gave us an asynchronous API here, but was it really non-blocking? This was the piece that was executing the Cassandra statement, returning the result set. As you can see from the highlighted comment, the author was rather confused by the need of using a Cassandra synchronous API when he clearly wanted this to be blocking. In fact, the word blocking appears twice in his comment, and I frankly don't think you can get more blocking than that. But where's that comment executed? It actually ran via Hystrix on dedicated thread pools. And for those of you that don't know, Hystrix is just a fault tolerance library built by Netflix. It's now deprecated, but it was popular in the past. And we were using up to 850 threads just for these Cassandra query operations in our more than 1,000 threads JVM. Each thread started the query execution and was then blocked waiting for the result to come by. With Eric's helping with parallel decomposition of work, we had multiple such threads started to the query execution in parallel and were then blocked waiting for the result. Making this non-blocking with Kotlin couldn't have been easier. All we had to do was to write a new execution strategy in our extensible library there that will run the query within a coroutine. But this coroutine is not created with an Eric's construct directly, but is rather with the coroutine's reactive integration bridge. And that's how we hook it up in the Eric's data flow. When this coroutine runs, we build the Cassandra statement, execute it asynchronously via the Cassandra driver, and then using the coroutine's Guava integration library, all we had to do is to call a wait on the driver result, which was a listenable feature. For timeouts, we've used Resilience4j, a highly popular fault tolerance library, and we're done. And with this simple change, instead of wasting that many threads, we could now run the same amount of work with just a few. So that was awesome. And more importantly for our goals, we managed to make the application at this point non-blocking end-to-end. Time for a quick timeline check. You will see this often. So we're now sometime at the beginning of week 3. Things were so smooth so far, we were quite confident that we could ship this prototype into production quite soon. It was time to evaluate it, though, first. We had to make sure that it works for more than just our test code. And for that, we benefited from a large code coverage with the integration tests. And these were framework agnostic, so we could use the same test even though we've changed the web framework. We spent most of our time in evaluating performance, And for this, we leveraged a load injecting system based on Gatling, which was firing requests against our application, and we were monitoring key metrics like error rate, latency, and saturation. We've started with a baseline throughput, which in this case was around 4K RPS for a lightweight endpoint that was doing a single Cassandra operation, and then we steadily increased that throughput in the load injecting system, trying to find the breaking point. And somehow, to our surprise, we've reached that breaking point quite earlier. So although we were targeting to have 1.5 to 2x throughput from the new application, already at 1.5x, we could see how the response latency was inconsistent at times. And going beyond 1.5x, the application stopped responding altogether. That wasn't great. So we clearly had a performance degradation as load increases. And that's somehow expected, right? You will not scale forever in a given resource declaration. But we also noticed something strange. As we were applying timeouts with the ARIX operator there, we noticed how the response latency from our Cassandra operation increased, and that led to plenty of timeouts. And of course, the server time for those operations was exactly the same. It was rather a local overhead that made all those timeouts appear. And we got some hints on memory allocations and GC pressure. It looked like our GC is actually running behind. So that was quite a blow, but we wanted to see what are our options to reduce the overhead. We could, of course, look into GC tuning at that point, but that's a complex operation and sometimes black magic, and also it's rather looking at the effects and not the root cause of the problem. We also considered switching to Cassandra driver timeouts, since we had a hint that the way we were handling timeouts currently had an effect on performance. But Cassandra driver timeouts are actually socket timeouts, and they were not delivering the same effect, since they were not bounding the overall transaction time. Finally, we looked at replacing Eric Java with Kotlin Flow in critical pieces of our data access API. Since we now had this complex stack with two reactive frameworks, we had coroutines, we had Erics there, and we also know at that time that even Kotlin Flow was young, it was outperforming Erics in certain benchmarks. And also, we wanted to have a coroutine native implementation in this critical path, so of course we chose Kotlin Flow. To better understand what exactly we've changed, let's dig a little bit further into data access API. We can actually split it into parts. A low-level API that was handling connection management and defining the query strategies that you saw earlier, and a high-level API where we're defining entity objects, data access objects, and data processors. The data access objects were used to access a single entity from one or multiple stores, while data processors were further refining those results. We wrote a new query executor with Kotlin Flow, as well as a complete rewrite of data access objects and data processors to use Kotlin Flow. For data processors, we kept the old ARIX interface, since they were the public surface of this API, and as we said at the beginning, we wanted to contain the changes and keep changes to a minimum as possible. This is the new query execution strategy that uses Kotlin Flow. As you can see from the signature, clearly returns a flow of results set now. It's no longer an ARIX construct. And when the flow runs, we build that statement, and then asynchronously execute it via the Cassandra driver, and then we simply suspend this flow and resume when the result comes by. Notice how time limiter and circuit breaker are simply decorating this operation now. At the end, we finally emit our result. We skip the data access objects and look into data processors, since they are a bit more interesting. As I said earlier, we kept the old interface here, so still returning a maybe, but this maybe is not created with the ARIX builders. There is rather the coroutines reactive integration library, or the builder from that, from that library, which essentially runs this in a coroutine. And when it runs, we use our data access object, which now returns a flow from which we get our first result. We're guaranteed to always have a result there. Also notice how additional work like instrumentation in this case, or error handling, is so much straightforward with Kotlin Flow. But did it work? Well, we believe this picture sums up our achievement with Kotlin Flow, since we were able to deliver better throughput from an API that ultimately looks the same. And as I said, we managed to hit our throughput targets with this, since it was performing better. But we also got a second benefit from this. The code was easier to follow now, since Kotlin Flow has an easier, simpler API, which is very similar to Kotlin collections that is so known. It's true on the other hand that we had to refactor more than we intended initially. We're still, if you look here, at 11% in this particular library, 11% Kotlin compared to 45% that is Java. If you look closely, we have quite a bunch of Groovy in there as well. Nobody is perfect, but those are in fact spoke tests written in Groovy, and that was a popular Groovy framework. We were now sometime at the end of week 3. We went through a lot, but we are still quite confident that we could ship this into production soon. And I will let my colleague Florentin talk you how about that journey.
Thank you, Radesh. In order to bring the new application to production, we established 3 checkpoints. The first one was to productize the POC. Second one would be to validate that all requests are processed exactly the same way as before, no functional regression. And also to validate that we are meeting our initial goal of increasing the throughput while maintaining the same request processing time. Although we had, after we productized the POC and we had the extensive integration tests that offered us confidence, we went a step further and tested the new version with live production traffic. And here we have our regular production setup, on top of which we added Go Replay, a tool which allows us to replay traffic in real time. And we are sending the same traffic to the new version, which was interacting with Cassandra in a read-only mode in order to not have side effects, but otherwise behaving as normal. By doing so, we have been able to collect transaction logs from both versions and compare them in order to spot any differences in processing. We are calling this the dark ages phase of this project, as we spent 2 months on productizing this POC, and most of the time has been spent on validation and debugging. Most cases have been edge cases which were impacting a really small percentage of traffic, and especially due to differences in processing between Jetty and Vertex. Nevertheless, it was a step which needed to be done. And now we are ready to release it out in the wild, and in each region, we would start with a canary to assess the performance, which is the non-functional side, and afterwards we will proceed with the blue-green deployment. And now we hit production, and although in our synthetic performance evaluations it performed well, in production and in certain regions it didn't. So it stopped at the canary phase, and we can notice that the Vertex version was processing less traffic than the old one, and this was due to a significant increase in processing time. So we didn't meet our initial goal of increasing the throughput, we actually made it worse. So we did a good old brainstorming. Remember, this is 2020, we didn't have ChatGPT to ask for help. So yeah, we sat down and came up with 3 tracks. One was to better understand the paradigm change, like how could the asynchronous request processing could have an impact in this performance regression. Understand the impact on our database, as now we have a higher concurrent request rate. And finally, it was to profile our application to identify any bottlenecks. The first thing that we noticed was that the task distribution across threads was unbalanced. The table shows the task queue size for each individual thread. What does this exactly mean, and what could the impact be? In synchronous processing, a request is represented by a single task, which gets processed by a single thread. In asynchronous request processing, a request can be represented by multiple tasks, which can be run by multiple threads. And these tasks are dispatched to a thread pool for execution. So in our case, task 1 could be executed by thread 1, while task 2 gets executed by thread 2. In the meantime, thread 1 is also executing a non-related task with our request. And task 3 gets assigned to thread 1, but before it gets executed, it needs to wait for the other non-related task to finish first. So basically, this unrelated task is impacting the actual latency of our request. In order to mitigate this, we changed the dispatcher to Kotlin dispatcher's default, which is implementing a work stealing algorithm that would allow for task 3 to be executed by another free thread. And in our case, task 3 could be executed by thread 2, maintaining the same request processing time as before. We noticed, after this change, we noticed a higher CPU usage, which was expected due to the extra work done by the work stealing algorithm, but no improvement overall. So we continue our investigation further, and we noticed that the Cassandra driver inside the application was reporting a high latency of 117 milliseconds, while the Cassandra servers were reporting sub-millisecond latency. So definitely something was going inside the application. We thought that maybe we would be subject of GC pressure, but collection poses were steady at 30 milliseconds, no spikes. So then we thought maybe some CPU contention. And you can notice from this graph that the CPU usage is around 30%, represented by the blue line, and the CPU load, represented by the yellow and green lines, is 10 on a machine with 36 CPU cores. So the CPU is quite free, no contention at all. Digging further, we noticed a metric reported by Cassandra called block task, which didn't sound well, right, as we wanted to be end-to-end on blocking. And these block tasks were actually requests that got rejected by Cassandra due to its queue being full. And the rejection happens by letting the client time out and not sending any response back. And this might have explained the high latency we were observing in the application. To mitigate this, we had two tracks. One was to increase the queue to be able for Cassandra to cope with our high rate traffic. And the other one was to limit the concurrency inside the application. We chose to increase the queue size as our goal was to increase the throughput, right? Unfortunately, neither this change presented any improvement. So our last track was to profile the application, and here we have a flame graph, which shows that our threads are most of the time sitting around waiting for work, as our code is barely visible in the two narrow lines on the right. Only after we took a recording with Java Flight Recorder, which gives us metrics with 1 second granularity, we were able to figure it out. And our application was affected by CPU contention, but during short periods of times. We didn't spot this from the get-go, as our regular metrics report an average over 15 seconds, which yield the 30% CPU usage we've seen before. So basically, our application is impacted by microbursting traffic, and during those short, intensive periods of time, we're actually blocking the event loop by exhausting all the available CPU. And the effects were increased in respect to the synchronous version due to how asynchronous request processing works. So now we had an application which was yielding a poorer performance from the original one. And maybe we hit a dead end with this project, and I'll let Raresh tell you further if we did it or not.
Yeah. Before we go into that, let's first look where we were at this point. So after the initial POC, we spent almost 2 months in what we call dark ages, fixing all the functional differences that we noticed. And then another 2 months trying to fit our non-functional requirements, or better said, understanding why we can't achieve them. It was a lot of effort put so far, and we weren't really sure when or even if we could ship this into production. The first thing we realized after our initial release attempt was that our workload was much more asymmetric than we've initially considered. We were focusing primarily on I/O heavy traffic, but it was clear at this point that we have quite a bunch of CPU intensive or requests that were both I/O and CPU intensive. And with the switch to asynchronous processing, we could now see an amplification of the effect across multiple in-flight requests. And that is in contrast with the isolation you get in a traditional one thread per request application. And it was particularly challenging for us in smaller regions where we didn't have enough spare capacity to even out the effects. What options did we really have? The first thing we thought of was to introduce a global application limit. And that was intended to limit the number of in-flight requests. The idea here was that when we have a CPU microburst, all the in-flight requests are prevented to make any progress, and that has a snowball effect on GC since the life set increases at that point. You have more things into memory. But that, even though this limit could have worked, it wasn't great since our initial goal was to increase the throughput of our application, not really put a limit on that. The other thing was to look into breaking the monolith. We had a quite old monolithic application. And the idea here is that if we could extract the CPU-intensive task and run it as a separate service, we can then have our web layer be doing mostly I/O. And that will ensure that we won't have a head-of-line blocking kind of problem where heavy traffic impacts regular traffic. So since this was a long-time dream of ours, we, of course, chose that. So starting from our existing architecture, the problem at this point lay somewhere in the business logics. Although it's depicted here as non-blocking, it was effectively blocking during those microbursts. So we took that segmentation, the heavy segmentation logic, out of the business logic, wrapped it in a Spring Boot application that we've deployed as a separate application, which exposes a gRPC endpoint. And we now call asynchronously from the web layer this application via an application load balancer. The obvious gain from that is that we were doing mostly I/O on the web layer. And we also managed to stabilize the response latency. We were now on a par with the blocking legacy application we had at the beginning. Although the throughput slightly increased in larger regions, we weren't able at this point to meet our cost reduction target. We merely get the 10% reduction. What that graph on the right-hand side wants to show is that for every web instance that we brought down with this change, we had to bring up an almost equally sized expressor instance, which was the new application we've built. How could we reduce the infrastructure even further? We had to look at this problem from a different angle. It was actually a fairness usage problem, since we had some requests that were 10 times the weight of a light one. It was true, on the other hand, that most of our requests were not heavy. Introducing more aggressive service limits were not possible at this point, since we couldn't apply them retroactively. But what we could do is to separate traffic based on weight, or the expected weight, or other factors like source. User-generated traffic is generally more latency sensitive than system-generated traffic. And if you have a way to somehow manage the two separately, then you can improve your overall application stability or even performance. And more importantly for our goals here, we were expecting from this change to get a further 20% reduction in the infrastructure footprint. From the previous architecture, all we had to do is to deploy a second target of our new expressor application that handles the CPU-heavy business logic, and then have a routing logic within the web layer that would choose one target or the other based on assigned quality of service classes, slow or fast. And with all these changes, we managed, after more than 6 months of work, to finally put the new applications into production and meet our goals. As I said earlier, or at the beginning, we almost doubled our throughput in the web layer, and we reduced the overall infrastructure with 25%. You may ask yourself at this point, was the effort really worth it? Well, it did because 25% translates into $1 million per year at our infrastructure footprint. But we also got a second benefit from this rewrite. The new application was now, the application we got initially was a 10 years old application. And with these changes, we were able to modernize it in critical places that has had significant impact. The application was now starting up faster and was using a smaller heap because all the metadata we had for the heavy segmentation business logic was now handled in a separate application. And that had significant impact on our overall stability and the performance of our application. But what were some lessons that we've learned from this experience? The first and very obvious one, and something that's probably true in all cases, try to change only one thing at a time. And this goes to our decision of using Vertex instead of sticking with Jetty. That led to all those functional differences where we spent almost 2 months to find a solution. The other thing is to use production traffic when assessing performance, especially for prototypes if you have the production traffic available. Remember how we chose to use a synthetic loading checklist system that wasn't really capture the true scale of or the weight of our request. We were simulating mainly I/O load at that point, didn't capture CPU heavy requests. Also trust but verify your metrics. You may not be very aware, but you may have implicit averages shown in your metrics, which are due to the resolution to which these metrics are captured in the first place. So having a way to have high resolution metrics, at least on demand, that's critical in latency sensitive applications. Also be aware of downstream impact of your changes. Remember how by going asynchronous, we've essentially opened the floodgates to our Cassandra service, hitting some service limits that we weren't aware of. Another one that might sound obvious, asynchronous improves throughput or latency, sometimes not both, unless you have a resource contention. You should have some power to drive it better. The point we are trying to make here is that switching to asynchronous processing alone is not going to be a magic solution that will make your application perform better. It's probably one of the ones that will have a weight on the result, but it's not the only factor you have to consider. Also, asymmetric workloads are bad, and you will notice that particularly in monolithic applications. And I know we live in the world of microservices, but there are still probably reasons to stick with a monolithic application. But if that application is faced with traffic that is asymmetric or that handles I/O and CPU at the same time, that is probably enough of a reason to think about splitting that application. And finally, hope for a short trip, but be prepared for the long run. And that is particularly true on legacy applications like we have. Most of the time when doing radical changes here will not be spent in the development phases, but rather in the validation and the deployment. But remember, all is not lost. Kotlin is your friend and was our friend in this journey. With a superb Java interop, you can do incremental changes, and that was instrumental, particularly in legacy projects like ours. And Kotlin Coroutines are really a complete stack for building asynchronous applications. I know the decision is harder now with Loom, but we believe Coroutines are the complete stack. And just think about how we've leveraged structured concurrency to help with context propagation in our juice implementations for asynchronous code. And another key point is that it really easily integrates with a lot of asynchronous libraries, anything you may have in your stack. For example, we've used the Coroutines Reactive, Coroutines Java, and Coroutines Guava integration library to bind in our existing code. And last but not least, use Kotlin Flow for modeling asynchronous data streams. Just like it did in our case, you may get better results than we would do with the alternatives. And you have really a cleaner API with it. We've reached the end of our story. We hope you've enjoyed it and you find a thing or two that might be useful for you in your project. Thank you for being with us, and don't forget to vote us.